hope it's okay. So yeah, we have Gereon here, and we will talk about approximate quantum error correction for symmetric noise. So please.
Yeah, okay, thank you very much for the opportunity to speak again here at Beyond ID this year. Yeah, this is joint work with Julius, he is here in the audience. Omar Fazi is in the audience, and yeah, okay, Mario has introduced himself. Let's discuss about something about approximate quantum error correction under symmetric noise. And yeah, I mean, I'll just briefly somehow continue on the discussion I had actually last year at Beyond ID about the underlying optimization problem. So give me a few minutes to introduce the optimization problem, and afterwards, yeah, we're going to discuss how to actually symmetrize optimization problems regarding approximate quantum error correction. So the problem statement is, as usual, we are considering noisy channel N, and yeah, our aim is to find encoder and decoder channels here called calligraphic epsilon and d. And yeah, an approximate quantum error correction, and that's a huge difference in comparison to zero error coding. We want to approximate somehow this concatenation of channels, so we actually need to define or need to align to a notion of approximativity, right? So we have to define in which sense we want to be approximately close to the identity in terms of yeah, HL to HL. Yeah, as we're motivated in a moment, and I'll just define it now, we'll just use the simplest notion of an approximate metric, that's channel fidelity, because, as we'll see in a moment, yeah, this problem can be reduced to somehow bilinear optimization problem, and in fact, this function, like the fidelity, becomes a trace because the maximal entangled set is a pure state, right? And then we can rewrite it as a fidelity, and the objective becomes linear, and that's somehow the reason why we're choosing that, actually. And to be honest, because we're here beyond ID, we can motivate it a bit differently, because yeah, there's a nice paper by Marco and Mario, it's 10 years back, I guess, but they have already somehow analytically discovered regions of these so-called achievable triples, and these achievable triples are actually defined with the channel fidelity. So what we are looking at is basically, or later on, if we can discuss symmetries, we are looking at yeah, symmetric channels, and basically bounds on the achievable region, which becomes somehow in the limit the quantum capacity. So it's in some sense, yeah, quantum coding with finite resources, as they have already did 10 years back. Good. Yeah, as I've said, we can rewrite the channel fidelity in terms of a bilinear optimization problem that's already known since 20 years. This is, for example, a paper by Renner. The interesting thing is, okay, we have here a bilinear optimization, so we want to optimize over the Choi matrix of the decoder and the encoder, and those are the usual Choi constraints, right? So in order to get actually quantum channels, we need positivity. There's equivalent to complete positivity, there's equivalent to the positivity of the Choi matrix, and those linear constraints, and actually they are becoming, they have a huge impact on the hierarchy we are considering in the next slide. Those linear constraints are basically the trace-preserving constraints, right? So we aim to get trace-preserving, or at least trace non-increasing channels, because otherwise it wouldn't be physical in a certain sense. Good. So this is the problem we want to study, actually. But now from the perspective of finding outer bounds, because like inner bounds are, I mean, you can always find inner bounds with seesaw methods, right? So you just optimize just on one hand the encoder and the decoder and so on and so forth. There's a seesaw argument, and this is actually done in that paper, I think, right? So the interesting thing is, what are the upper bounds? And they correspond actually to that achievable region for the quantum capacity. Good. Yeah, as I've said last year at Beyond ID in the coffee breaks, I actually had many discussions about the convex optimization problem because it's an SCP hierarchy, and the question was, why can't we just apply a DPS type of hierarchy? Like the DPS type of hierarchy would just consider that problem and would enforce, just on the first level, basically, the linear constraints. And that motivated us within the last year to make it somehow mathematically to give a rigorous distinction between these two hierarchies. And that's what we want to discuss now. So let me define this sigma prod. This is basically the feasible set of the underlying bilinear optimization problem. So we just consider the convex closure of product states which satisfy the Choi constraints. And yeah, I mean, actually, the goal of our STP hierarchy is to approximate that set from the outside, right? So an STP hierarchy is nothing more than, yeah, considering perhaps not STP representable set and to approximate that set from outside. And that means we can rewrite our optimization problem for the channel fidelity as nothing more as this one, right? So we just optimize over states out of that set, and yeah, rho LP, LP bar, L bar, B bar is now out of that set. And due to a linearity argument and the linearity of that trace here, right? Yeah, the convexity is not a problem. So that would be the problem we want to look at, actually. So we want to somehow find out the bounds to that. And now, there's known STP hierarchy. This is a paper by Mario and Oma. And they have shown that we can define STP representable outer approximations, and these are given by positivity states, permutation symmetry, because a definite argument tells us in the limit we'll get actually something like separable states. And the important thing, and that's something which we want to study for that moment, is that here we have these miraculous constraints where we have to add somehow the extension, or here in that constraint we have the first n-1 extensions, and then we have the kind of decoupling in tensor product, right? So this is kind of a bit unnatural if you just consider that problem in terms of, for example, a DPS hierarchy, because in a DPS hierarchy, you would just write it like that, correct? And the question we have discussed last year, and actually there's an example in the origin paper already, was are they actually different, or can we somehow understand the difference between the set sigma sep, which is exactly the same set as sigma prod, just replacing these somehow different constraints, right? So here we are just considering something like an average constraint, right? Good. This defines a slightly different STP hierarchy. It's not difficult to apply the same proof technique as they have done in the paper from Mario and Oma to see that the sigma sep hierarchy converges. It's exactly the same argument. You can just apply the definite theorem. It's a finite definite theorem. Actually, the linear constraints, I mean, it's similar, the proof technique, as here. And that tells us that both STP hierarchies converge. And the last question would be, okay, what are the difference between the channel fidelity and that? Good. We took one step back, actually, and just rewrote that question in the most simplest way, what we are usually doing if we want to answer a question on like an abstract level. Yeah, the question is whether the minimal tensor product of two cones and a linear constraint, so first applying a linear constraint, then a minimal tensor product, or first applying the minimal tensor product and then applying a linear constraint, if these two operations commute, right? This is basically the question of these two hierarchies. On one hierarchy, in the bilinear optimization hierarchy, we basically do that on the left-hand side, and the other hierarchy, we do that one, right? So basically, we apply the min tensor product and then apply a linear constraint, and that's, the question is, are those operations commuting, right? That's basically the mathematical question behind. The answer is no. Okay, not surprising, but I think if one considers such an somewhat abstract example, it makes somehow progress in understanding where is the proper difference of these STP hierarchies, right? So usually we want to somehow enforce conditions on average for the DPS hierarchy, for example, because we are just interested in really the marginals, for example. But in the bilinear optimization hierarchy, we are really interested in a decomposition, right? So we really want to enforce that in each summand of a decomposition, the product state satisfy the constraints. And this can be done actually by observing that these two operations do not commute. Good. This somehow, the motivation, and as I said, like a continuation of some coffee break discussions from last year. But anyways, for the talk today, where we want to actually calculate stuff and want to do some math with the symmetries inside of those programs. So we just have to consider that hierarchy, and the argument is as shown, right? So we know that they are not equal to both hierarchies, and this hierarchy is the appropriate one. Just the last comment. If you want to properly implement that, I think it's a tough task, but we have to enforce something like a permutation symmetry, and we have these constraints, and these constraints grow a priori by exponentially in n, right? So this is nothing more than exponentially large state in n. So we have exponentially many equality constraints if you write them line by line, each equality constraint. So basically the task is considering that problem and to solve it, but with a small caveat, and that is, now, okay, we want to somehow include a bit more of structure into the noisy channel, right? So at the moment, we are just considering a noisy channel between P and P bar, and that might be everything, but our aim is to restrict that noisy channel M to N to somehow, for example, an IID, copies of IID channels or something to get bounds on that achievable region. Good. So, yeah, as usual, if you have an SCP and you have symmetries, you ask the question, can I reduce the symmetry? So basically, can I reduce the dimension, or in other words, can I reduce the number of free variables? And let me introduce the picture we want to consider now. It's the following picture. So again, our setup. Our setup is given a noisy channel, and our noisy channel is something now in that coding scheme, right? So just n copies of I don't know. Let's assume a bit flip channel or amplitude damping or whatever. And the question is, can we find, or like, can we come up with outer bounds for given encoder, so for finding encoder decoders in that SCP hierarchy, right? And for that particular case, we can ask, what is the symmetry of that IID tensor power in that picture of subsystems, right? If you want to symmetrize an STP, you need to invoke, in a certain sense, how does the group act on the Hilbert space, right? So there's an action, and we somehow have to study that action. And I want to explain that action on that picture. Here, this is a subsystem picture of that coding scheme. Actually, those are P1 bar, P2 head, like an upscript bar, and those are all the extensions, right? So from left to the right, those are the extensions, and then an extendability hierarchy. And we want to encode this tensor power. This is somehow from above to the bottom. So this is something like the IID symmetry, but the IID symmetry, how we call that later on, of that channel somehow commutes, or like, permutes P1 with P2 simultaneously with P1 bar and P2 bar. So it actually acts on the first two columns from the left and permutes row-wise, and the extendability symmetry from the STP hierarchy, it permutes column-wise, right? But it starts just here, right? Another observation, because, yeah, I mean, like, we want to be somehow, we want to include all the symmetries which are available, because, yeah, if you want to calculate something, you really need to reduce the dimension, as we will see in a moment. Another symmetry we can invoke is something like here, an isotropic state symmetry, because, if you push a maximally entangled state through the channel, you get an isotropic state channel symmetry in the L system. So there's another symmetry, and this is something like, okay, on those two L bar systems is a maximally entangled state, and this is an isotropic state, and this has thus a U star symmetry, right? So the question is basically, given this symmetry, given the IID symmetry, given the extension, the permutation symmetry, can we somehow combine them in an STP in order to get dimension reduction, right? A discussion about that, because I want to remark that that work in that direction was already done by Huang Ta from Singapore. Is the point is, if you encode one qubit into m qubits and you just consider the extendability symmetry, then you can just make a dimension estimate, and this was done. Basically, the results there have shown that you can basically apply standard symmetry reduction tools in order to reduce the dimension of the extendability symmetry, as you would have done in DPS hierarchy, for example. But then you calculate the overall dimension. It's not difficult to see that. And if you have just one extension, and that's somehow our aim at the first place is just to go beyond that PPT channel coding situation, right? We just want to have at least one extension. More would be much better, but I mean, at least one extension would give us better bounds, strictly better bounds than just PPT. But the point is, if you just have one extension, the symmetry group is the S2, right? And the S2 has two irreducibles, so the trivial one, the sign representation, and then you can estimate the two blocks you would get, right? Just two blocks, but they are already pretty large for just one qubit and 3 qubits, right? So if you just go to the simplest situation, and that is like the simplest non-trivial one, right? So 1 into 1 is somehow okay, and we can discuss, but it might be a bit boring. 1 into 2, we know actually for many channels that the trivial encoding decoding operations are still optimal, but for 1 to 3, for example, there's this somehow hidden problem for amplitude damping channels where we know, okay, it's unknown basically what's happening, right? So the interesting question is at least 1 qubit into 3 qubits and one extension because of that PPT result, right? But for that particular case, you can calculate the dimensions, and the dimensions are already in the magnitude of 2000. And yeah, if you try to solve that in an STP with many constraints, it might be hard, right? So the result of that discussion is really, okay, we have different symmetries at hand, or we can at least include them. Can we somehow make profit out of that? Good. Let me recall that problem. So the bilinear optimization problem, actually. Given M tensor n, right, so we can rewrite that C M tensor M. Here you see the Choi matrix. This has now this IID symmetry as shown in the picture before. This is the maximally entangled state, actually. And this is the optimization variable. And what we would like to do now is we just would like to apply a first or second hierarchy extension of that. Yeah, as I've said, we have now these basically three types of symmetries. And there's a natural question coming up, and that question is, in like, again, mathematical language, given such an STP, H is something like our Choi matrix, so H has the IID symmetry and isotropic state symmetry, and rho is an abstract language, something like our optimization variable, and from that we have that extendability symmetry, right? So rho has to be unextendable, and the Choi matrix has inherently those other two symmetries, and the question is thus, given that we have an STP such that H and maybe the constraints satisfy some symmetry, so are basically in the commutant of the star algebra, and similarly rho is in the commutant of another star algebra, can we make benefit out of both symmetries, right? This is the abstract mathematical question we aim to answer, and it turns out it's, yeah, it's non-trivial actually. To be concrete, given U and V, we want to come up with the compact group W, and that it is a group is actually important, right? So we want to apply this Peter-Wald theorem at the end somehow to get this block decomposition. Now we want to build up or cook up a group W out of U and V such that these inner products are satisfied. And the point I want to emphasize is it's properly different to lead the inner products invariant instead of just having on the level of matrices equality in terms of commutativity, right? So neither rho or H has to be somehow has to commute with W, or is in the commutant of the star algebra of W, right? So the important thing is really that this fact that W leads the inner product invariant is weaker, it's strictly weaker than being in a commutant, right? That's somewhat the observation. Now, if you have such a W, or if you have a resub to come up with W out of U and V, we can play the usual game. And the usual game is, yeah, okay, we have that STP, we can twill, and we can define something like dimension reduction. Yeah, as said, the general problem is somehow a bit difficult to come up with the W, just in total generality from U and V. For our purposes, for our correction, it turns out that it's enough to consider W of that form. Yeah, so we consider a group W, like we consider something like an object W out of products, and we just enforce that W is a group. So by definition, we call it strong symmetry reduction, or we call an SCP exhibits a joint symmetry reduction if and only if W and this formula is a group, right? And for that question, we have somehow nice answers, in which cases we can come up with W. But just as a remark, if you have W like that, like always as products U and V, you can just insert that here, right? And you see, okay, U goes to the left, V goes to the right, and then you have that rho and H are in their commutants. So the inner products stay invariant under this W in case this is a group. And as said, you need that it's a group because you want to apply that dimension reduction argument with this block decomposition argument by Peter-Wald. Okay, great. So let's study that object. So in which cases or which situations for U and V are somehow appropriate. Now, first of all, some mathematical hints that it's a somehow well-defined object. If U and V are closed subgroups, then W is compact. Okay, that's a continuity argument. If U and V commute, that's somehow a usual case we aim to consider, and the intersection is trivial, then okay, it's somehow a nice situation from group theoretical point of view. It's just a direct product, and and as said already, and just here it's listed as a lemma. If you have such a W and as a group, then the inner products stay invariant. So somehow this notion of W seems to be at least well defined. Let's study conditions under which W actually is a group. And it turns out that W is a group in the sense of that joint symmetry reduction, if and only if it commutes as sets. So if U, V, VU, if you consider all these sets, all these elements, and they are equal as sets. So basically, such a somehow weak commutativity assumption. It's not a commutativity, right? So be aware that that's not commutativity. It's really something like a weak commutativity. If this is true, then W is a group, and we can apply our framework. There's one result. Another one is, if one of them normalizes the other one in the group theoretical sense, you can easily come up with that with the standard result in group theory. That's okay. You find a semi-direct product out of that. If one of them normalizes the other, then it's of course a group, and we know in particular the concrete structure of that group. And for finite groups, and we make use of that in particular for the IID symmetry and the extendability symmetry, you have that formula. If U and V form a group, then there's this product formula for the cardinality. So those three criteria are actually somewhat useful in order to decide whether dimension reduction with the notion of joint symmetry reduction, as I've introduced, is applicable or not. Let's go back to error correction. And error correction, as I've shown you, there's this picture where the Choi matrix is invariant on the IID symmetry and the isotropic state symmetry, and we have the extendability symmetry. And in this theorem, we start with just studying their combined actions, right? So we're just studying, okay, given the IID symmetry acting on the first two columns, given the extendability symmetry, they together span a group, of course, because they're both subgroups of the unitary group, so there has to be something like a joint group. And it turns out that you can even calculate or prove the isomorphism type of that group. And this is somehow a group extension of AM, okay, if you have M extensions, and the root product of SM and SN. And that means if that short exact sequence splits, that G is isomorphic to a semi-direct product of AM and SM with SN. And that means that this group G, if you compare that to SM and SN, recall SM is just the IID symmetry, SN is just the extendability symmetry, it's a pretty large group, right? And that means we find as a corollary that this group is much too large. Right? If you just insert the plain definitions or the plain actions of the groups of the IID and the extendability symmetry, it turns out that this group has cardinality, Sm to the power of n times, so the cardinality of Sm to the power of n times cardinality of Sn times cardinality of Am. So this is much larger than Sm times Sn, right? So it's much larger than we would expect from the criteria for finite groups for dimension reduction, right? Good. That's a general no-go theorem in terms of, okay, if you just insert the plain actions as they are and then try to figure out what's happening as subgroups of the unitary group, then we see that this group is too large. Nevertheless, there's a solution. As we have now understood somehow, kind of in which directions we have to look for this joint actions. And we have seen that, okay, plain methods have somehow this non-trivial kernel, if you consider that AM and that group extension as a kernel action. I mean, it basically turns out that you can come up with something much simpler, which falls into that picture. And this is what we call a commutative relaxation. Just again, that picture. The case I have shown you so far was, okay, we really invoke that the IID symmetry acts as it would act just on the Choi matrix, that is on the first two columns, and the extendability symmetry acts on all of them. And the theorem I've shown you tells us, okay, the joint group out of them is much too large. What we can do now is we can extend somehow the action of the SM by permuting the rows to all of the extensions. And the reason for that is that we can use the partial trace as nothing more than adding an identity and tracing afterwards. That means if you relax the action of the IID symmetry to all over the extensions, and similar for the isotropic state symmetry, if you relax that diagonal action of UU star to all of the extensions, we find somehow that they commute, right? So we basically simplify everything, so it becomes a much smaller group actually. But it turns out that they commute, and if you recall our results, the commutative case for the joint action, it was basically the simplest one, right? So if the symmetry from H and AJ in an SDP and the symmetry of rho, if they commute, then you're basically in a direct product case, and for that we can easily write down the dimension reduction. Good, let's do that. you can basically prove that proposition. I call that enlarged invariance, but it tells you basically, okay, given these extensions, then you find for the IID symmetry a diagonal action, you find for the for an internal channel symmetry a relaxation, like if you just insert something like, okay, each qubit has an internal symmetry, you can relax that, and even though and in addition, you can just extend the isotropic state symmetry all over the copies over the U's, right? And this is C. So basically, we find 3 groups, and they all commute, so we can easily combine them in that joint symmetry reduction framework. Yeah, writing that down leads us to the following SDP. The SDP now has again here CPP is, oh here is a bar missing actually, is invariant under an SM, but as said, we extend the SN action to the identity. VLL L bar is a maximally entangled state. We extend that to a diagonal action over all L systems, and we have that usual extendability symmetry. And the result is that this SDP becomes an invariant under an SN, SM, and an isotropic state symmetry. But recall, the important thing is, or like we have to notice that this group is much smaller than this group we have considered before, right? So we basically lose something in terms of the size of the group. But we win in the sense that we can just solve the problem. Okay, fine. Yeah, if you do that, if you remember these numbers, I've said to you in the 131 example, if you just use the extendability symmetry, you have 2 blocks of size 2000 and 2000 roughly, right? If you do that with the much, like somehow refined symmetries, you find that table sorted in irreps of the S3, U2, and S2. Okay, I mean, just some names for all these irreps, but I mean that's known things, right? But then you find that you get 12 blocks for one extension, of course, right? With those sizes, and I think it's appropriate, right? So we can implement that actually. So this is doable. We can implement this SDP. It's a bit hard, so actually it takes a few hours to calculate each point, but it's even doable at my home. So I think it's somehow. Yeah, we can come up with bounds on the channel fidelity. I gave you here one example, or I've brought one example. This is the IID amplitude damping noise on 3 qubits, so 1 qubit into 3 qubits back to 1. Okay, now one has to include many other things, for example, non-signaling conditions from Bob to Alice and Alice to Bob. That's not done here, so they're just SDP constraints. I wasn't. Actually, to be honest, I figured that out afterwards, after I did that calculations, that I have to include both. Here I just included once. So what I've done here is basically symmetry reduction and PPT plus 1 non-signaling, but not both. So it's not the strongest results you can achieve, but it's easy to extend those to the strongest results you can achieve in just adding that simple SDP constraint, and it's not difficult. But yeah, as you see, this is the bound which was known before our work. So this was that PPT bound for almost 10 years or something. And the green line is somehow our new bound on level 2. But yeah, I think even conceptually, it's somehow interesting that it's possible to go beyond level 1, even though the SDP, of course, grows not in the best way. Yeah, as I've said, maybe, I don't know, 1 or 2 minutes left. Let's discuss some outlook. Yeah, in the manuscript, okay, I hope we'll upload it at some point in the next days, weeks, I don't know. That contains many more examples of channels with symmetries, but usually without numerics. So I just calculated the numerics for the amplitude damping and the depolarizing noise, I think. There we have results similar to the plot. But of course, you can now just combine your favorite symmetries, right? So you have the extendability symmetry, that's what you always need because of the extendability hierarchy, but there's this IID symmetry, there's an isotropic state symmetry, and you can even think about, for example, internal symmetries of the channel, right? So let's say we have a 1 qubit channel and tensor power that, and we know that this channel has somehow a covariance with respect to another symmetry, right? Then our results say, okay, you can include them in an SDP, and then you can apply exactly the same tricks I've shown you here. And in particular, for some examples, we give quantitative statements that you somehow reduce stuff to an LP plus a few 2x2 SDP blocks or something. Another thing which I find interesting actually, and if you were in Aachen last week, I asked exactly the same question in Felix's talk. The framework doesn't work just for IID, right? So you can just invoke a permutation invariant channel. And the question, like at least from that channel coding perspective, which I think it's not too bad actually, is to consider channels which are not tensor powers of IID. So have something like, let's say we disturb them with a C0 or something. Then you should get, I think so, quantitatively a slightly different plot. Maybe it would be interesting to discover or like to investigate this direction for a while. And yeah, I mean, I have to do that joke, right? It's beyond ID then. Okay. And the general framework of symmetry reduction, actually, I'm not aware at the moment of really nice examples where you have non-trivial interactions. So I can cook up one. You can easily cook up examples if you just consider natural actions on n-dimensional Hilbert spaces, and you can just consider them as subgroups of the symmetric group Sn, and then you can combine them in non-trivial manners, and of course, and then you see, okay, it's usable. But in applications, I don't know, I think maybe there's a nice path forward in order to consider something like the Lacerre NPA hierarchy or even graph relaxation problems. Maybe there at some point such combined symmetry problems occur. It would be nice to see them. Actually, I don't know yet, but maybe one of you have had an idea. And as a last point, I missed one thing over the whole story, and that is how to implement the matrix entries efficiently, right? So if you really want to write on the SDP at the end, you have to somehow do one exponentially expensive step, and this is a matrix multiplication step, right? And for all these nice results, in order to say something like, okay, we can implement something efficiently, there's a very nice result by these three people, like under the supervision, I think, from Alexander Shiva, who have shown that for particular groups like Sn, like the extendability symmetry, or particularly the Reith product, it's doable that one really calculates each entry in the resulting SDP efficiently. And it would be nice to see now whether those techniques can be somewhat extended to, let's say, more general groups or groups which are useful in that framework. Okay, thank you very much for your attention, and happy to hear your questions.
Thanks, Gereon. Do we have questions?
So in the spirit of error correcting codes, can you flip this around and impose fidelity 1 and learn something about the performance of quantum error correcting codes? I mean, this wouldn't be working for tensor power noise, but it would still be permutation symmetric.
How should that, like, okay, you would give a constraint on the objective, right? So
yeah, exactly.
But wouldn't that
for error correcting codes, you know, you fix the distance and like sort of you only allow that d of the qubits are affected.
Wouldn't that be infeasible somehow for many cases?
Yeah, I suppose so.
Yeah, okay, I think one can impose such a constraint, but in the usual case, I think it's infeasible. But okay, if you want to prove something like a statement in terms of, okay, no code exists,
yeah, exactly.
Yeah, okay, maybe I think about that actually, but okay, yeah, maybe you can do that, yeah, because the hierarchy comes from the outside, or so if the first level is already infeasible.
Yes, exactly.
Okay, yeah, I have to think about that. No definite answer. I'm sorry about that. Thank you very much.
Thanks, Andreas. Any last minute question? Good, then let's thank Gereon again.